We're going to get going here on the lightning talks. The rules are 5 minutes a talk. I will tell you when you have 1 minute left. We're taking questions at the very end of everybody's talk, so hold them, and you can attack the speakers at that point. So with that, we have Lang, I think, to kick it off with PBQP.
All right. Thanks, Chris. As Chris said, my name's Lang, and I'm here today with Arnaud to give you an update on PBQP register allocation in LLVM. I'm going to kick it off with a quick background of PBQP and an overview of the cost model. And Arnaud is going to describe his experience using this allocator in the wild. So, quick bit of background. PBQP was born out of DSP compiler research. And the aim was to find an allocation method that would make it easy to deal with the complex constraints that frequently come up on DSPs and embedded systems. And this is not a new allocator. This has been in LLVM since version 2.4, so that's 2008. It's been applied to about half a dozen architectures that I'm aware of. It allocates the whole nightly test suite, sort of getting somewhat mature at this point. And the appeal of PBQP, at least to me, is that it has a very straightforward way of expressing the register allocation problem through a simple cost model. So we'll take a look at that. So for each variable in your machine function, you are going to create a one-dimensional lookup table that describes the cost of each of the register allocation constraints for that variable. So if you have a variable A, and you could spill it or put it in register R0 or R1, you have a one-dimensional table with one entry for the spill, one for R0, one for R1. And say in this example, you estimate that it's going to cost you 50 cycles worth of load and store code if you spill A to memory, 0 cycles to put it in R0, and 5 cycles to put it in R1. Presumably there's a longer instruction encoding somewhere that slows you down if you choose R1. So one-dimensional cost model isn't sufficient, though, to model the register allocation problem. So between each pair of variables in your machine function, so we got two variables, A and B, each with their own one-dimensional lookup tables. We introduce a two-dimensional lookup table between them to describe dependent constraints. So here we're modeling interference. The axes of this matrix are the allocation options for register A and register B. To model interference, you simply say that it's going to cost you infinite costs if you try and put these interfering virtual registers in the same physical register. The PBQP allocator is going to go away, and it's going to try and find a register assignment that minimizes the costs expressed in your model. You don't have to fully construct your cost model yourself. LLVM will, out of the box, give you spill costs, spill costs, interference, and coalescing constraints. And then you can override a target hook to add custom constraints for your target on top of these. Now, Arnaud has done this for a couple of architectures now, and I'm going to hand over to him to describe his experience working with the allocator.
Okay,
Arnaud?
thanks, Lang. So my very first experience with the PBQP was about 2 years ago in a previous life, because now I'm working for ARM. This is not an ARM CPU. We had an extremely small CPU with a 16 bits encoding instruction set, and we had 16 bits integer registers. And beside that, we had many 4-register operands domain-specific instructions. So, as is obvious, this cannot be encoded in 16 bits. So we had to come up with a way to pass the third and the fourth operands implicitly. And this was encoded as the successors. For example, the third operand is the successor register of the first operand, and the fourth operand is the successor register of the second. Great. The first problem that we found out is coalescing, because the coalescer is not aware of our constraints, and pairing requires different registers. The problem is that the coalescer will have coalesced happily those pairs if they hold the same value. So the very first thing which we had to do was to undo the coalescer's work for those instructions. And of course, we have to do that smartly, because register is a scarce resource, and we have to spare that. And of course, at the time that you insert those copies, you must not also forget to update the liveness information. So now we have all the registers that we need to set the PBQP constraints. So let's set them. So the obvious constraint which we have to set is the pairing constraint, where one register is the successor of the other. That's quite obvious. Now, that's not enough. The problem is that the pairing constraint is transitive. What I mean there is that if you have one pair of register and you have a second pair of register, then if one element in the pair is shared, then now we have a relationship between those two registers. And this has to be described in the constraint set. If your constraint graph is not complete or consistent, then the PBQP solver will give you some strange results. So this was my experience about 2 years ago. And since then, there has been quite some work on the PBQP. And so there has been some work on composable constraints. So it makes it really easy for target to express their own specific constraints. There has been also some work on improving many different aspects, like reduce a lot the memory consumption of the allocator, like reduce a lot the compilation time, and last but not least, also improve allocation quality. So when we speak about compilation time and allocation quality, I will show you some numbers. And for those numbers, I've chosen to use the ARM's Cortex A57. So when using the PBQP, we somehow trade off compilation time for allocation quality. So how much compilation time do we have to trade off? Here I ran the compilation for a number of spec benchmark. And on geomean, PBQP is about 17 slower than greedy for the Cortex A57. So it's acceptable given if we can have a better allocation quality. So how do we measure allocation quality? There are several metrics out there, but the one which I have chosen for this presentation is the one which we all care about in the end, and that's execution speed. So with the PBQP, how fast is my executable compared to an executable generated with a greedy allocator? So here is what we have. The 100% line means that PBQP and greedy are on par. And we can see that for some executables, we really get a big improvement. And we also have some regressions, let's say that like that. And I've analyzed them, and it just turns out that the way spilling is done is the most basic way you can think of. And by reusing the LLVM spill placement infrastructure, we can bring a very substantial improvement to this allocation quality. So expect soon some improvement to come about this allocation quality.
Hi. So this talk's sort of an invitation to try this infrastructure out now. It's been in tree for a while. But the Achilles heel was always the solver time and the memory overhead. We're working hard to bring those down. And especially if you have an exotic architecture that you have difficulty allocating for with the default allocators, PBQP might make it a lot easier to deal with your target. As we said, we've made it very easy to customize. There's just one target hook that you now have to override to get access to the PBQP cost model and to add your own costs on top of that. So very easy to customize. And please try it out, get in touch with us. We're happy to help you figure out how to port this to your architecture. All right.
Thank you, guys. Okay, the next speaker is Yunzhong Gao from Sony to talk about link time optimization on the PS4.
Hello, my name is Gao. I work with Sony Computer Entertainment. I am here to talk about link time optimization implemented in the PS4 linker. Last year, I gave a talk on LTO without the linker support. We used a combination of LVM link, LLC, and opt. Okay, I'll restart. So I'm here to talk about link time optimization implemented in the PS4 linker. Last year, I gave a talk on LTO without linker support. We used a combination of LVM link, opt, and LLC to achieve LTO. It was simple to implement, but had some disadvantages. For example, we had to change the source files to mark some symbols as attribute used because opt does not see all the external references to all the symbols. The initial evaluation showed great results, so we went ahead and implemented LTO in our proprietary linker. Before I go on, I would like to thank all of you who contributed to LTO. This talk would not be possible without your work, so thank you. Now back to our linker. The linker separates the input files into native objects and bitcode files. Each bitcode file is scanned for symbol references and dependent libraries. They are added for compilation by calling LTO codegen add module. The native objects are also scanned for symbol references. After the scanning phase, the linker has enough information to resolve all the symbols, so it does that. In the compile phase, the linker marks all the symbols that need to be reserved in the bitcode files and compiles the bitcode files into one big native object. Some bitcode symbols that were not marked as reserved might get deleted in this step. The linker updates the symbol references after compilation. After that, the linking steps continue as usual. Now we have LTO calls all over the place in the linker code base. So how to debug LTO problems or how we even assign bugs to the appropriate teams becomes a challenge. To make this less of a problem, we used a separate wrapper process to relay LTO calls between the linker and LTO.dll. One advantage of doing that, if there is ever a crash inside the LTO library, the linker does not immediately crash as well. It can try to recover or at least print a nicer error message. The wrapper implementation is kept simple. It is a lot easier to debug than a complete linker. We gave the linker the capability to save a list of LTO commands so that we can replay the LTO interactions later when an error happens. This also allows us to write unit tests for the LTO library. We tried this LTO implementation on some of our games, and we got some numbers. All games reported some runtime improvement ranging from 1.43% to 9%. Most of the runtime performance gain is obtained in the inliner, internalized global symbols, and IPS CCP passes. We got mixed results for the executable size. Some games grew by a few small percent, although there is one game that got 11.8% improvement. We believe that the inlining threshold and dead stripping are responsible for the fluctuation. Build time generally increased with LTO from 3 times to 10 times without debug info. One game team reported they tried LTO with debug info turned on. They gave up after 30 minutes when the build was still going on. So here are some related work items we are interested in continued discussion and improvement. So one is that we noticed LTO builds with debug info use a lot of memory, take a long time. And that is still the case, even though we saw large improvement from LVM 3.3 to 3.4. So we are very interested in ideas how to reduce memory footprint in this area. We would like to add versioning to LVM IR so that the LTO library can detect IR incompatibility and handle them better. We have a patch under review. And further performance gains in LTO. For example, maybe it will make sense to reorganize some of the optimization passes in the compiler. In conclusion, we implemented LTO. It worked for us. We recommend more people to try LTO and make it better. Thank you.
Next up, Peng Cheng will be talking about LLVM for interactive modeling and high-performance simulation.
Hello, everyone. I'm Peng, and this is Dale. And today I will talk about our recent work using LLVM for interactive modeling and high-performance simulation at MathWorks. And so we have a poster session outside. So after that, if you have questions, you can just come in to us. MathWorks provide multi-domain model-based design for systems from multiple industries. Specifically, to model a system like this DC motor from the physical modeling domain, we will first build a Simulink model and click this button. The model will get compiled and executed and to get the results. A very common design question is that whether a new part, like this inductor here, will get the system better or not. So this question can be answered by simply plug this new part into the model, click this button again, and analyzing the results, and you can figure out your answer. So it's very important trying to reduce the time between the click and the final simulation results. So in this talk, we will focus on how to using LLVM for that. And before jumping into technical details, I will define two terms. A model means the entire system, and a component means just a part of the system, like this inductor. So a model contains many components. So the model used to be simulated using shared libraries. So if a model wants to compute a state, so if you ask its components, so hey, inductor, so what's your state? So the inductor will look on the disk and looking for its shared library. So if it's there, if you load the shared library and the compute state and return to the model. So otherwise, it will get the equation, generate C code, write C code on the disk, and compile C code in the shared library, and then finally load the shared library to compute state. So apparently, this involves many expensive disk I/O. And what's more important, and both the equation info and error info used to generate the execution code are lost. So this prevents global model optimizations, such as variable elimination, index reduction, so on and so forth, leading to locally optimized execution code and high-cost interactive modeling. So using LLVM, so the model will not ask its component to compute state. Instead, it will combine the component equations into model equation, and then generate LLVM IR, and optimize it, and then JIT into machine code to compute the state. So if we want to compute different type of states, so we will trigger multiple threads to handle that. So this enables us to do global optimization in model equation, global optimization in LLVM IR. There is no disk I/O involved, leading to globally optimized execution code and low-cost interactive modeling. And now we have a LLVM-based backend running reliably in production code. So producing consistent numerical results. We are supporting multiple threads on multiple platforms, and we are pushing for adding global optimizations into the new simulation engine. So performance, so execution time performance is about 10% faster than old one. For compile time performance, about 10% slower than old one using pre-compiled shell library, about 10% faster if the shell library are not pre-computed. And we are expecting more performance improvement when the global optimization are in place. So overall, we have a great experiences with LLVM throughout our entire project, but we also ran into a few challenges. First one is the shell library support. So we have different use cases for LLVM, so leading to multiple linkage of static library in our code base. That's very painful. So the second challenge is that the JIT performance. So the JIT time is now is a bottleneck for our compile time performance. So the third challenge is how can we propagate exceptions through the JIT code. And the last challenge is how can we smoothly transition from the legacy JIT to the MC JIT. Thank you.
Next up, we have address sanitizer for Windows from Timur I.
Okay, so hello, my name is Timur Iskhadjanov. I'm here to talk about address sanitizer for Windows. In case you don't know, address sanitizer is a memory error detector which is capable of finding bugs like heap buffer overflows or use of freed memory. And it was designed from scratch to get high performance and scale well for large apps, for example, compared to Valgrind. And it was originally developed for Linux with more OSs in the works now. Let me very briefly describe how it works. In case you're interested, please read the original paper on the topic. So basically, for each memory access, we check if the address we are accessing is OK to use. If it's not, we print out the report and crash. To do that, we have to hold some state for the application memory, and we are able to actually encode a state of aligned 8 bytes in just one shadow byte of memory, which allows us to use a very simple function to translate from application address to shadow memory address. And since this is a simple function, we are able to produce very efficient instrumentation, which is performed at LLVM IR level. This comes at a little cost, which is we have to map the shadow memory as a large bulk of data in the middle of the virtual address space, and we have to do it really early before any shared object is loaded or any large piece of data is loaded. The other thing ASan has to do to work correctly is to intercept a few functions. So basically, we have to intercept memory allocation functions to track where memory comes from, where it goes. We also have to intercept a few functions just to detect more errors or to understand what exactly the app does, like when does it create threads and stuff like that. Where's the stack? So when we eventually think that there's an error, we grab the current stack trace, we try our best to find the exact memory allocation this address came from. We try to get some extra information about this allocation, like where was it allocated, where was it deallocated, and stuff like that, and print every useful information to the user and terminate the process. So we all like Linux. We're compiler guys after all, but it turns out that most of our desktop users are actually using a different operating system. So we've decided that it would be very useful to get ASan goodness to Windows. And to prioritize better, our first goal was to find the nasty security bugs in Chromium browser. We started a couple of years ago, and in the middle of this year, we got to the beta experience, which is most stuff works well. There are a few rough edges, but one can work around them or send patches. Welcome, by the way. So let me briefly describe the progress. Good news is that since the instrumentation was done at IR level, there were no significant changes required at all to the instrumentation module. We have to significantly change the runtime library because it was originally very POSIX specific, and just Win32 API is significantly different from POSIX, as most of you probably know. And we spent a huge amount of time on C++ ABI on Windows. So basically, even now we cannot compile every single translation unit of Chromium, so we had to get to some compatibility bar so we could build some translation units with Visual Studio and link them together with address sanitizer instrumented code. One other thing I'd like to talk about is C runtime. So on Windows, there are at least 4 commodity runtime libraries, like static linkage, dynamic linkage, release, debug, and all the possible combinations. And each CRT is differently structured and uses a slightly different code. So each one requires separate handling. We currently support only the release versions of the runtime library. One interesting thing to keep in mind compared to POSIX, for example, is that on Windows, each shared object, or DLL, could have its own instance of the C runtime, which includes, for example, the memory allocator state. So how do we handle the static runtime? In the main executable, we just define functions like malloc, which we want to intercept, and the linker does the job for us. It just forgets about the system definition and uses our own one. However, we also use some functions that are DLL imported, like create thread from kernel 32, and we have to hot patch it before it is executed for the first time. Also, as I said earlier, we have to allocate the shadow memory range as early as possible in the process lifetime. So we do that while executing the first memory allocation call in the CRT initialization. In the DLL, we just define the same set of functions and redirect calls to the main executable implementations. The dynamic runtime also has to hot patch the dynamic DLL runtime. So we build our ASan runtime as a DLL with as few dependencies as possible, so it's initialized early in the process lifetime before the C runtime is initialized. One other thing I'd like to talk about is debug info. So ASan reports are next to useless without file names, line numbers, function names. And LLVM wasn't doing a very good job on that front when we started. So as part of the project, we had to add a generator for minimal line table to COF object writer in LLVM. And it pretty much works now. And as an almost free bonus, we are now able to debug ASan generated and Clang generated binaries with Visual Studio or WinDBG, like step in, step out, step over. But unfortunately, we cannot look up variable values yet. We've successfully deployed a Windows ASan to Chromium and specifically to clusterfuzz, which is a huge testing infrastructure which finds security and stability bugs in Chromium. And we've already found more than 50 bugs in Chrome in just 3 months. We're also working with other open source projects. Last thing I want to show is that, in fact, I was showing this talk in a browser instrumented with ASan. So if I just try to print the presentation, I've introduced a small bug. It's a heap use after free. If I change the printer, it actually crashes. So you can see a fully functional browser with an ASan instrumentation. Thanks for watching, and please try Diagonalizer on your Windows app if you have one. Thank you.
Harsh? I think we're looking for Harsh. Yeah. All right. Next up is Harsh Devedi. All right. Software Visualizer, a tool for visually exploring the Linux kernel with Clang. All right.
Hi, guys. I'm Harsh from Qualcomm. So Qualcomm, we do a lot of Linux kernel development for all kinds of devices. And so I'm here to talk about software visualizer relating to that. So first of all, what is Swiz? Swiz is a system. It's a collection of, it's a tool to generate a program call graph and be able to query that and be able to get the data out of that. And it should be relevant to every single developer who has to solve bugs. The idea with Swiz is you should be able to triage bugs really fast, and you should be able to get to the bottom of the problem without spending time on searching for things. And so what happened with us was we get all these kernel bugs, and you get the log, and it says, hey, this crash happened on function X. Now, if this function X was something that you've been familiar with, then that's good. But on many occasions, what happens is that function X is something that you really don't know, and then you start running your grep, and then you start figuring out, oh, what is X, and where is it getting called from? And that's pretty much, I think, searching for what the context of X is, where it's getting called from. That probably forms, I think, a huge chunk of debugging effort involved. And so I was compiling kernel with GCC, and then I was interested one day to compile the kernel with Clang, and I compiled the kernel with Clang, and I came across this this utility I think that Clang offers, which is it prints out these the call graph of every single file that you compile, and that was something really interesting that I came across. And so what we decided to do was we decided to use that call graph printer pass from Clang to generate the call graph for each individual file, and then stitch together all these call graph files that Clang generates to get the full program call graph. And eventually, you can have this repository of, basically, you can have this full program call graph, and you can query that with a simple web front end to get whatever data you want. There was another point in there where you wanted to stitch together all these call graphs. So the idea was to make it as simple as possible. I mean, you don't want to introduce a huge step or some huge overhead just to generate this. So it should be really, really easy. So you get the call graph from one file, and then you have the call graph from another file. You want to stitch them together. So instead of reinventing the the stitching together of thing, what best you can do is you can probably just piggyback on the linker itself, and so you invoke your call graph stitching from linker, and that gives you this advantage that you don't have to duplicate linker's functionality. So if you have a function x that's getting called in call graph 1, you want to know where this symbol x is getting resolved from. So what you do is you just hook into the linker symbol table, and you basically ask, hey, where is x getting resolved from? And once you figure that out, you stitch together x to whatever node this the linker has resolved it from. So it kind of saves you the the trouble of doing that stuff. So how does it work? Basically, what you're doing is when you get the object file, along with object file, we also generate a dot file, which is the call graph for that object file. And because eventually what you do is you combine your object files to, and you give it to the linker. Linker generates the output program. What you do is you take the linker, your script actually gets invoked from the linker, and so it stitches together the dot files also, and eventually, along with the program, you also get the call graph of the full program. So there's nothing extra to be done over there. Once you get the call graph, you want to be able to view that. And so the idea was, again, over there, not to have some special piece of software to do that. So I looked into making a web front end. And as long as you have a browser, you can just start viewing interacting with it. For being able to view and manipulate the graphs, we used a Python NetworkX library, which makes it really, really easy. I can just give a small demo of how the tool works. So let's say there is something happened in some function called Adreno start, and that's a function that your crash is happening on. So the first thing you do is you start to figure out, hey, where is Adreno start getting called from? So what you can do is you can query the full program call graph, and you can just specify a depth, let's say 1, and you just say go. And basically what happens is we extract the subgraph around Adreno start to the depth that you specified, and it says this is the subgraph around that depth. You can increase the depth, and you can see further still, you can query the graph deeper. And what happens in this case is, as you can see, the graph explodes the moment you do depth equal to 2. And this is what I meant when I said, you grep for things, and then you're like, oh, God, this is where it's getting called from. There is another scenario that happens very frequently, which is you get incomplete logs, and you ask for logs, and people say, well, this is all it is. You have to work with this. And so you basically get sometimes a source function, and you have a destination function and something, and you really don't know how it could have gotten from source A to B, and you have no idea. So first, what you do is you start figuring out all the paths that could have led from point A to point B. And then you start figuring out which possible path could have actually done this. Well, the idea, again, over there is that you should not be working on figuring out the paths. The paths should be calculated for you. And so that's what we implemented there. So let's say, this is your source function, which is, and let's say we have a destination function. And say, once you have the source and destination function, what you do is you just say, search for me, and it tells you there are 6 paths between these 2 functions, and you can basically immediately look at what all paths are there. From there, all you have to do is you can work on your part, which is just analysis of the problem. Thank you.
Great, thank you. Next up, we have automatic loop diagonalization by Vedant Kumar.
Okay, so hi, my name is Vedant, and I'm going to talk about a neat application of linear algebra to compiler optimization. So hope you have fun with this. Fair warning, there's a bit of math involved. Okay, so the main idea of my talk is that there's this equivalence between certain loops and matrices, and we're going to exploit that by using the formula for fast matrix exponentiation. And then we'll talk about how you can put that inside of your compiler. And if I have time, a demo. So some loops can be fully described by a matrix. So let's look at one of the most famous loops of all time, the iterative process for computing Fibonacci numbers. What's happening here is that we're updating the state vector AB, and the new version of A gets 1 copy of the old version of B, and the new version of B gets 1 copy of the old version of A plus 1 copy of the old version of B. And that can be encoded with this matrix formulation, right? So if you squint really closely at the entries of the matrix, it's exactly what it's saying with respect to the 1 copy of this and the 2 copies of that. And yeah, so with this, what you can actually do now is you can get rid of the entire loop. You can just raise the matrix to the appropriate power, and then apply that matrix to your state vector, and then you get back the Fibonacci number that you want, right? So if you do this naively, you end up with a big O of nm cubed time bound. And thanks to math, we can do better. So you start off with the standard eigenvector equation. You collect the eigenvectors of your matrix in the matrix P, and the eigenvalues in the matrix D. You factor it, so you get m equals PDP inverse. So this is the diagonalization step. Okay, so the fun part is where you start taking powers of the matrix, right? If you square it, you get PDP inverse times PDP inverse, the p's cancel, and then you end up with PD squared. And the neat trick is that it's really cheap to compute powers of a diagonal matrix. You can do that very fast, right? So with induction, basically with any power, any number of iterations of the loop that we want to compute, we can do that in much faster than linear time. We do it in logarithmic time with the repeated squaring algorithm. So that's what we're going to teach the compiler to do. We just get rid of the loop, stick in a diagonalization, and we get a much better time bound, because now you just do 2 matrix multiplies and 1 diagonal matrix exponentiation, which, so you have m eigenvalues, and then you do repeated squaring m times. So you've taken an iterative process that runs in effectively big O of n time, and the compiler knows now to run it in big O of log n time, right? And the trick is that you can see the middle matrix there, phi to the n, 1 minus phi to the n. You only have to raise the eigenvalues to the nth power. So, okay, so that's what this optimization pass does. It looks at loops that it can't handle. So not all loops are like the Fibonacci loop, right? Life would be great if that were true, but it's not. And right, it does a depth first search on the basic block that contains the loop body to figure out the coefficients of that update matrix that you saw. And it uses the eigen library to get the eigen decomposition. It takes all of the state variables flowing out of the loop, and then it replaces them with the ones that it computed, and then it gets rid of the loop entirely. And that's the end. I have a demo, though, so right. So first of all, this is LLVM 3.4. It's still a work in progress to port it to trunk. But what's happening here is that we have the standard version of the Fibonacci routine. Forgive me, I had to use floating point numbers to make it work with eigen. But we have a loop preheader, the loop body, and then a back edge, right? So that's a standard loop. And then once you diagonalize it, you get rid of the loop entirely, and you just have this 2 matrix multiplies and the eigen decomposition in the middle here. And you can benchmark it if you like. It runs much faster. But so just a fun example of what you can do with a little bit of math. Thank you.
That was pretty awesome. You should run that on GPUs because they like floating point adds and multipliers. That was our last talk, so I want to thank all the speakers. And if you have questions, I think they'll all be up here. So please come up. Thank you.